when a ketone or aldehyde is treated with aqueous hydrocyanic acid, which is HCN here, the product is a cyanohydrin. And so when we talk about cyanohydrins, that's just a molecule where you have an OH group and a cyano group. And remember, a cyano group is the CN, okay? And they're bonded to the same carbon, right? And we can see that right here. So this is an example of a cyanohydrin. Now, cyanohydrin formation is important for two big reasons. First, it's another valuable carbon-carbon bond forming reaction, and so it gives us an additional way to construct large carbon backbones if we need to. Second, the carbon-nitrogen triple bond functional group, which is a lot of times shortened to this, but remember there's a triple bond in here, is pretty easily transformed into CO2H, which is a shortened way, just to remind you, a shortened way to show a carboxylic acid, okay? And I want to show you, this is the C in there. So you can see some of the shorthand here. Now, this type of reaction is called a hydrolysis reaction. It's written here for you. And the overall product is what we consider a alpha hydroxy acid. Now, those compounds, particularly the alpha hydroxy acids, are useful in synthesis, but also some of those alpha hydroxy acids, such as glycolic acid, are used to treat a lot of skin ailments, right? And so this is something that we see pretty frequently. Now, in this overall reaction of HCN with a carbonyl group, the cyano group adds to the carbonyl carbon and a hydrogen adds to the carbonyl oxygen. And that both of those things are shown in red here, okay? So here's your carbonyl carbon, and we're adding the cyano group to it, and then we have the hydrogen here being added to the oxygen to form an alcohol functional group. Let's look at this mechanism. And so as we look at this mechanism, we first start out with the acid here, okay? And what happens is it reacts with water in such a way where, it's just a general acid-base reaction, where the water comes out and it steals, acts as a base, and it steals that proton, and those electrons go onto the carbon. Now, this generates our nucleophile here, okay, for our nucleophilic addition reaction. And so that will go on and if we have a carbonyl carbon, we'll attack there, and those electrons will go there in that first nucleophilic addition step. Then it will go on and undergo a proton transfer. It will go there, and those electrons will go there. And we end up with our cyanohydrin. Now, and we've regenerated our nucleophile. Now, I want to point out a few things about this. And one of the big things I want to point out here is there's really a very small amount of NC minus present. Okay, it's very, very small. That's why I gave the equilibrium arrows like I did. So the equilibrium really lies over here. So anything that we can do to get more of this will speed up the reaction. And just to kind of give you an idea, only about 0.001% dissociate into NC minus. That's it. So to make this reaction more effective, we can add a catalyst. And the catalyst that we add is KCN, okay? And that's an ionic compound. So when we look at KCN, it's an ionic compound and it will dissociate into K plus and Cn minus. And so it increases the amount of Cn minus that we have in solution. And then the OH here from sodium hydroxide will deprotonate HCN, so OH minus, also deprotonates HCN quantitatively, like at 100%, right? So notice here, right, and you can go back and look at the previous slide, that the NC minus is generated in either of these ways won't be consumed during the course of the reaction. And so that means that we consider both KCN and NaOH as catalysts because they increase the amount of Cn minus. Now, like negatively charged nucleophiles, uncharged nucleophiles can attack alpha beta unsaturated carbonyls at 2 locations. So we saw this in the last chapter and it's back again. So you can get the direct addition product, which we also talked about as the 1,2 addition product. And you can also have an attack at the beta carbon to give the conjugate addition product, which is the 1,4. Now, there's a trend that we see though, and that trend is that uncharged nucleophiles heavily favor conjugate addition over direct addition. Right? And so we can see that here, right? So remember that conjugate addition is the 1,4 where the nucleophile is added to the beta carbon. And so that's the product that we see here at 95%. Okay, and so we get 95% of that product. Let's look at the mechanism for how this works. So when we look at this mechanism, let's start by drawing our molecules. These electrons are going to come in and they're going to attack the beta carbon there. When that occurs, these electrons are going to go here and those electrons are going to go up on the oxygen. So that's nucleophilic addition. We're going to follow our arrows, and we see that the sulfur, the thiol group here, adds to the beta carbon, like that. Then we're going to undergo a proton transfer. With water. where these electrons are going to come and grab that proton, and those electrons are going to go back on the oxygen. Right? And then we're going to undergo another proton transfer. Where these electrons are going to steal that proton, and those electrons are going to go on the sulfur. And then what we notice here is that this is the enol form, and this will undergo an enol keto rearrangement. So it'll undergo that tautomerization. And give us the ketone back, right? So, frequently what we find is the addition of uncharged nucleophiles to the alpha beta unsaturated carbon, like what we see here, right? This is a nucleophile that doesn't have a charge. Doesn't require acidic conditions. Unlike direct addition, conjugate addition of an uncharged nucleophile proceeds at a pretty reasonable rate. Mostly, and the reason for that is because we end up with some resonance stabilization in the enolate ion, and I was a little low when I made my circle. In the enolate ion, that is produced here in the first step. So this is resonance stabilized, so the activation energy isn't quite as high for this reaction. And so it proceeds at like I said, a fairly reasonable rate. Now, HCN, which we started looking at, right, also adds to the alpha beta unsaturated carbonyl compounds by a similar conjugate addition, okay? And the reason is because the addition of the NC minus to the carbonyl group is reversible. And so one example is the reaction that's shown here. And so we see that, again, that group is added to the beta carbon here through the conjugate addition, or the 1,4 addition. So this works in a very similar way to what we've seen before.